So I gave an assignment, right? I gave an assignment, and some of you have done it. So and sent it to me through my email. So means that I mean over half of the class have done it. So I assume that you guys have all seen it. So, huh? Not that I updated the site with some slides and then an assignment, homework. And then I even gave a date for the homework. So it means that if you open it, if you were able to open it. But as I said, some of you have submitted it, so that's what I'm going to use. And I gave a deadline for the time and everything and stuff like that. But it wouldn't have been an issue if some of you had not submitted it. But once some of you have submitted it, then so let's continue. Are you all clear? Pardon? Inform you. I update the site almost every week before the class, like 2 days before the class. So if you check there, you will see all the slides there. There's some homeworks and stuff like that. And then in the homeworks, once you open, there's a deadline and how to submit. It would have been an issue if some of you have not submitted. Then I would say, oh, let me update you quickly. But some of you have submitted. So when, wait time did you go there? But wait. Have you seen the new slides? And then and you didn't see any homework there. Some of you have submitted. I can't really do it. It's about half, like about 20 something. So and it's like some 5 months or something like that. Very very easy. You submitted, right? You submitted. You submitted. Ask him. And then I think he also submitted. Okay, so let's continue. So far, this is VLSI and embedded systems, right? For the first part, what we did is the embedded part of the course, right? Now we are going into the VLSI part. That is strictly for the computer engineering guys. Right? And then this is going to be very, very quick, like very fast because all I'm going to talk about, you guys have done it before. So I hope that we will finish everything today. And I keep it time. Yes, you can see it. Ah, really? Okay, I hear. Okay, so pay attention, right? So I said the first part was the embedded part. So I taught you how to use the Arduino boards and stuff like that, right? How to program it, how to write code using, and then how to call digital pins, analog pins, and stuff like that, right? And I taught you some interfaces, I2C, UART, and then TWART, right? I taught you how to do all of this. Now, those ones were the embedded systems part, right? High level language, you write it and you program the board. So where we are going right now is the board itself, the microcontroller itself, right? Each component there is made up of a chip. So we are going to see how those chips are made. Understood? So that's the VLSI part. And then I believe that you guys have done this already, so I will go very, very fast. Man, I think you guys, the evening guys said they've done it. I mean, logic design and stuff like that. Yeah? Uh, okay, so 50% of the marks will be embedded, then 50% will be VLSI. So if you want, you can leave and take only the embedded system course and take a 50%. I mean, it's so pass mark, right? And if you attend the classes and stuff like that, it's still pass mark. Shall I continue on? So now we are going to see, and then I think in the first lecture, or something like that, I was telling you how we built up from the transistor level to what? A very, very complex system. So now we are going to see how to start from transistors, the lowest level of your chip, to logic gates and stuff like that, to the AND gates, OR gates and stuff like that. Like, so how are they made? Right? So, so the high level overview will be at the end of the day, right? You should be able to design something like this from the scratch, from the ground up, using only schematics, AND gates, OR gates, XOR gates, and stuff like that. You should be able to design this. Who knows what this is? Looking at the individual components inside there, what is it? What is it? So this is typically a CPU, the one found on your Arduino board, right? Just one chip, the CPU of your Arduino board. This is how it looks like, and I believe that you guys know each component here. You know that each CPU has memory. Each CPU has a register file. Each CPU has an ALU. So you should be able to design this from the ground up using logic gates. That's what you're going to see. So each component, how to design each component from the ground up. I mean, at the end of the day, we should have been taught how to use HDLs to design this. How to use HDLs to design this. But because there's but be- because there's no time, you just design it from the schematic level, right? And then I think that's even easier than using the HDL. So you guys will all pass the course degree, right? I mean, those who fail will fail. It doesn't. All right. So if you check the architecture of this, right, we have two memories. Have you seen it? We have one memory over there. Have you seen it? And then we have another memory here. Why do you think? Why do we have two memories? Why do we have two memories? One here, one here. This is a typical CPU. We have two memories here. Why do we have two? Why not just one memory? One for what? Yeah. Okay. So half. I'll give you half. Uh-huh. I mean, you guys are. I think you guys are usually losing marks by not answering questions. So far, no one also answered questions, right? Only this girl and then some other few. Right? So why do you have two? Yeah. Massa. Why do you have two memories? The computer engineers. So, in a typical CPU, right, what is a memory used for? In a typical CPU, what is a memory used for? Hmm? What is the use of memory in a CPU?
To store information so that when you need to run an app, like allocation, data allocation,
Do what?
data allocation.
Data location. So you guys don't know a typical memory, what memory is used for. So when you write your program for, let's say your high-level program, C, right, it gets converted to what? Machine language, right? So where is that machine language stored? In part of the memory. So the machine language, you know that the machine language is made up of zeros and ones. But we have fields within that zeros and ones. And each field has a meaning, right? So one field is for part of the field is for instructions. So the instruction part is stored in one of the memories. Instructions like do addition, do subtraction, do multiplication, do this, do this. It's stored in one of the memories. While the data part is stored in another memory. So typically we have instructions memory and what? Data memory. Simple, right? Instruction memory, data memory. So instruction memory is fetched from the instructions is fetched from the what? Instruction memory. And then it will be decoded by the what? CPU. Then it will execute and then it will probably write back some data to the data memory or to the data memory. Easy as that. So now you can see that if you pay attention, right, this is the instruction memory. And this is the what? And this is what? Data memory. Now pay attention to the ports. If you see here, we have only one port here. But if you look at we have two ports, D in and D out. But here we have only one port. That is like an output port. I pay attention. So why do you think we have only one port here?
So you said
I mean,
this is an instruction. This is the instruction memory, right?
are you asking me what I'm telling you?
I want to before I
From who?
from you before I answer the
But I said it. So why are you?
so it has to read the instruction from the circuit and then read out. So let's say we have our instruction is to add or let's say copy a file from here. So it goes there.
Next person.
This has to do because
Uh-huh.
one will be used for reading and the other will be used for writing.
Of course, I mean,
And then this one just reads.
so that one asking why?
Why does it? Because it's just reading. But
Just
this one
reading.
has to read and write. This one is not reading and writing.
So why is it not reading and writing? So why is it just one point? Yeah.
It's because the instructions within this memory are in such a way that they are fixed.
They are what?
They are actually fixed.
Yeah.
They are fixed to perform certain calculations. For example, if I want to do addition, instructions here are actually fixed for addition, for performing addition.
The further you go, the further you are drifting away from. But once you say fixed, like, I mean, I'll take it. But as you explain more, then you are nearing zero. If you started from 5, then you were going, as you explain more, and you right? So now, in your typical CPU, in your typical PCs, you have ROM, right? And you have what? RAM. Is the ROM fixed or not? ROM, read only memory. So you can only read from the ROM. You cannot write to the ROM. So that's why we have instruction memory. You can only read from it. You cannot write to it. But for the RAM, normally you can write and read to the RAM, right? So what happens is that during execution, right? Once you're able to once you write your program into the instruction memory, right? That's it. You cannot write to it anymore because once you begin to tamper with the instruction memory, you will have an issue. So they always make it only one port, so so that you can only read instruction from it. You read instruction, but for the data memory, you can write data to it during execution, right? Probably you are doing x is equals to a plus b. A is stored somewhere, so A will be pulled out, do some calculation, then store back the results in then store back results. So this one has to have two ports, one for writing and reading, because during execution you can write to it and then you can read to it. But for this one, instruction memory, you only read from it, right? Shall we continue? I hope you are all there. In the exam, if I ask you all these things, then I mean, you guys know what this code is. A very very simple. What type of code is it? C, a very simple C code, right? And then how does the code work? So what happens? What happens if you write a code like this? What happens? What tools do you use to convert what to what to what? That's what I want the process from your low level to your hardware level. How does it work? Low, high level language, right? To your low level, the machine language. How does it work? A code like this. What tools are you going to use to actually convert this code? You guys have done C, C++, Java, whatever, whatever. So let's see the process from this code to your machine level. You answer.
Is that what we should remember? Or this is still
Average.
yeah, Martha.
You guys are how many?
At least five.
But,
So you always get this number.
yeah, average. Yeah.
So mark attendance. They feel those ones.
Oh, yeah. I have the attendance every week. 5 marks every for each lecture. All right, so let's go. How do we convert this code from this level to the low level to the lowest level, the machine language? It will compile. So what does the compiler do? People still do this. I still have to eh.
It converts the two to assembly languages.
So we have a compiler, right? That will take your high level language and then convert it to what? Assembly language. You guys don't know this process. That's what the compiler does. Then from there, what happens? Then, so you know that the assembly language is not the lowest form, right? The lowest form is zeros and ones, but the assembly language is like something like R0, R1, R3, something like this, and stuff like that. So this is not the lowest level. So after you have compiled and then you have converted the code from the high level language to assembly, then what? What tool do you use to convert? Assembler, right? You use the assembler to convert from the assembly language to the machine language. Easy as that, right? Now, you must know that each, um, every industry or every institution that makes CPU has their own language. Every institution, right? Or every company that makes CPU have their own language. But what is essential is that each CPU must have these components, right? Memory, register for ALU, and stuff like that. But how they are arranged It's what will separate an Intel CPU from probably from the others, right? How they are arranged. But each CPU must have all this. So the language of the CPU is known as the assembly language, right? And the assembly language is different from each CPU. That's why you cannot use the assembly language of Intel CPUs to go and run on another CPU. It won't work because the hardware is arranged completely differently. The same number of the same thing, but it's arranged differently, right? Each industry is trying to look for something in their hardware, right? Some are going to, some are actually going to optimize for speed. So if I want speed, right, my CPU is going to be completely different. The internal architecture is going to be completely different from the person who is looking for less hardware area, right? Someone speed fast, someone less hardware area. So all of this will actually determine what. And then even so, we know that we have different forms of architectures for our CPUs, right? We have two types. They are what? The types of CPU we have. How many?
Say one human architecture.
For Newman architecture, and then what? And then what? You have for Newman architecture type of CPU, Harvard architecture, right? So there are two types. What is this type? You have no type. What is this type? Huh? Why? That's why I said your foundation, your background is your background is you know some terms, right? But you don't actually the most important part of the term, like the meaning of the term. Probably you just know it, but you don't see it. You can't visualize it. You can't imagine it, right? So if I say this architecture is Harvard architecture, you know what Harvard architecture is. What is the meaning of Harvard architecture from your own? Listen. We have von Neumann and Harvard. So this architecture is actually Harvard architecture, right? Now the difference is that, as I said, if we take your machine language, right, it comprises of both your data and then it comprises of your instructions, right? So we have data. Data will be separated from instruction, right? We have data and instructions. Instructions and data. Pay attention. Instructions, data, right? So are we there? Remove your pens and then your thing, and then tell us to continue. Then I can continue for you. So we have data and instructions within your machine code, right? So how do we store this data and then how do we store these instructions? Now, some CPUs store the data and then the instruction in the same memory, right?
Yes.
So you have other components. So you have your memory like this, right? And then they'll divide the memory into two. Part of it will be for what? Data, and part of it will be for what? Instruction, right? So this is von Neumann architecture, right? Where you store your data and then your instruction in the same memory, just one memory, right? Now, so how do you think you can access data and then instruction? What will separate your data from your instruction? So how will I know that? Oh, I read from this location. I read from location 0, and then that location is instruction or is data. How will I know? Hmm? Yeah, so the addressing, right? So what happens is that you address a portion of the memory to be what? Instructions, and then you address a portion to be data. Easy as that, right? So now the issue with this is that for memory, you can only read one location at a time. If you see this picture, it's just numbers, 0, 1, 2, 3, going, right? These are known as the addresses. 0, it means that there's something within location 0. 1, now you can only read from one location at a time. 0, 1, 2, 3, 4, 5, going. So what if I want to read instructions and data at the same time? Then I'll have an issue, right? But the most important thing is that this makes your code very, very simple because you have only one memory to address, right? But you can only address one memory location at a time. You can only read from one location. That's just the main issue with the volume one, right? It's slow because you cannot read from you cannot read an instruction and data at the same time. You only have one port, so you have your main control here, and then you have only one port, right? That reads instructions and data through this port, only one. So, but for the Harvard architecture, right, we store data in one location, in one memory, and then we store instruction in another memory. So if you have your control here, right, you can read, there are two ports for both instruction and data. So here, I can read instruction and data at the exact same time. So this makes it very fast. But again, this makes your hardware use more gates because now you have two memories instead of just one memory. Are you seeing the differences? Von Neumann uses less gates because it has only one memory. Harvard uses two memories, right? So more gates, right? Von Neumann is slower because you can only read one at a time, one instruction and then one data at a time. Harvard is faster because you can read instruction and data at the same time. I read it. Shall we continue? Any questions so far? Okay, so the main point is that when you take your C code, just like something like this, int x is equals to 10, x is equals to 2 times x plus 2. So just double x and add what? 15 and then store it in what? X. Very simple C code, right? Right? So the compiler will convert this code, this simple code to the assembly language. And I said the assembly language is the language of the CPU. Right? But that's not the lowest level. So this is how the assembly language will look like. Add R5, R0, 10, MULI, R5, R5, 2, and then R5, R5, 15. I hope you guys can understand what it is. Very, very simple. And then this is the same as this. I hope you can see the differences. Or I mean, I hope you can see that they are actually the same. Shall we continue? So now, after that, we convert using the assembly. We convert this to your machine code. So you see that there are 3 lines here, right? These 3 lines correspond to what? Those 3 lines over there. So these are not just some random zeros and ones. Each field means something, right? But interesting. Each, each field means something. These are not just random. And I believe that you guys have done something like this before. Whatever. So, The what? Put it that one. So this code. So you should know. Why you laughing? You should know how to convert this assembly language to machine code, but that doesn't matter. I won't be bringing all of this, so don't worry about yourself. But the most important thing is that this assembly language or this machine code will be stored in your instruction memory, and then it will be fetched. You know that all the CPU does is that it fetches instructions, then it does what? Fetch instruction, then what? Huh? It fetches, it decodes the instruction, then what? It executes the instruction, then what? Then what? Then what? Then what? Then what? Write back to memory. Master, why are you laughing like that? Is it wrong? I mean, if I mean to go deep, you guys' head will just explode. That's why I'm just taking it like the basic level. It doesn't just be like this. So. Okay, so the most important thing is that, right? Your instructions are stored here, right? So one at a time, you read the instruction, you decode it. So this control here will decode. So it will separate that machine code. You saw the machine code. It's a 32-bit number, right? So the control here will separate all the fields. There is a field that will tell you that, oh, this instruction is addition or subtraction or whatever. And then there's a field that will tell you that this read from this register, write to this register, and stuff like that. So this control will decode it. And then some of the values will be sent to the ALU. That is if it requires that it's an addition. It will send to the ALU, it will do the addition, then after that it will write back to the register file. So fetch, decode, execute, write back. Fetch the instruction, decode, execute, then write back. Have you seen it? Which one? Have you seen it? Okay, so you know the ISA is just the assembly language. And as I said, the ISA is just the language of the. So it serves as an interface between your software and then the hardware and stuff like that. Uh, you guys know that every system, a computer system has something like this. A computer system has a computing unit, a communication unit, and then what? Memory or storage unit. I won't go into that. So, and then, as I said, we have the volume architecture. I explained it here. You have the Harvard architecture and stuff like that for your main CPUs, right? Okay. So now, for this course, right, what you studied in the embedded is the top part, application part. You write your high-level language, your sketches, your Arduino sketches, and then it will be converted using your compilers or whatever. Right? Now, the middle here is the IAC. That is the language of the CPU. That's what the CPU can understand. The assembly language, right? And then you have what is down here, the hardware itself. You have what? IO memory and stuff like that. Data path, can control, data design, circuit design, right? So what we're going to study right now is below. We have done what is on top already. The sketches that you wrote, right? You guys know how they work. Now we are going below and see how the hardware also works. Right? Are we there? Very, very easy. I mean, I've brought it to your level, not to your level, actually. I've brought it to junior high school level. Oh, I mean, if I mean to bring it to your level, only one person will pass. Me. Okay, okay. So pay attention. So this is where we are. We are going to study the micro architecture and then the logic, right? And then that is your course. That is the course for the that is your main course, computer engineers, right? Now let's begin. The first thing we will study here is the transistors. As I said, the transistors is the basics of the basic, right? That device is what is used to make all your device, your watch that you're wearing, probably your phone, probably your pacemaker in your heart. You have one, right? Yeah. Right? So this is the basics. This is where it started from. This is what a transistor looks like. And then you know that a transistor is what? It's like a switch, like your switches here. What you do with the switch is that you can turn it what on and what? That's it. So that's what a transistor does. A transistor can come on or it can go off based on the voltage you apply to it. Understood? All right. So, but the most important thing is that for transistors, right? So, okay, so look at this here. The first CPU was Intel 4004, right? It was made in 19 what? 71. It has 2300 transistors, right? So the Morse means what? What does Morse mean? You guys have seen it somewhere.
Yes, we are seeing it somewhere.
Okay, okay. Metal oxide semiconductor.
Yes.
Right, so just pay attention. The first one was 1971. It has 23,000, what? 2,300, right?
Yes.
Transistors in 1971, right? The next one was in 2000, we have Pentium 4.
Yeah.
And then it was made up of 42 million transistors.
Yes, sir.
So you see the differences in transistors from 2300 to what? 42 million in 2000. Then in 2022, we have the Apple M2 Max. It has what? 67 billion transistors, right? So how is this possible? How? So you know that your devices are getting smaller, but the transistors are increasing.
Yeah.
So if you take a typical die, if you take, let's say a chip, let me bring it to your level, a chip. If you take a typical chip like this, the same chip area, right? In 1971, we had 2300 transistors. Now, for this same chip area, in 2000, it increased to 42 million transistors on the same chip area. Then in 2022, it increased to what? 67 billion, right? So, what are they doing? How are they able to pack so many transistors within the same chip area? They are what? Decreasing the size. Simple as that, right? They're decreasing the size of the transistors. So it means that they have more. What? What?
Electrical.
Uh, okay, I'm going
We have electrical students. They are
I'm too young to be involved in anything. Alright, so they are simply reducing the sizes of the transistors. Right? It's as simple as that. I mean, you see how you are even actually good at all the computer engineering guys. Right? So this is how the transistor looks like. We have a metal, we have an oxide, and then we have a semiconductor. grouped in. I hope you guys have seen this before. So then typically the transistor has, it looks like this. We have the gate, we have the source, we have the what? The drain. So what happens is that English language, right? Gate. If you say gate, what does that mean? Right? So if I say a gate, what do I mean by that? And then relate your English language to digital systems. Right? This is how the transistor looks like. Something like this. You have a gate, you have your source, you have your drain. So what happens is that, like a gate, right? Like your switch, right? You apply the right voltage, you apply voltage through the gate, and then it will allow current to flow from the source to the drain. That is if the gate is closed or not. You know what the gate is. You close the gate, you open the gate, or a closed circuit or an open circuit. Once you close it, you know the current flows. I mean, you guys, right? Right? So here, if you, once you apply the right voltage to the gate will close here, and then it will allow current to flow from the source to the drain. Are we there? You have seen this before, right? You have not seen this before. Okay, so the most important thing is that we have two types of transistors. We have what is known as the N type. We won't go to the just the surface level. N type and then what? P type. So for the N type, right? If I take the N type, this is very very simple. This is just basics. So if once I take the N type, this is how it looks like. Gate, source, drain. Now, in case I apply voltage here, right, it will close or open the gate based on whether it is N type or P type. Right? So if I apply, let's say 3 volts here, for the N type, applying 3 volts will close the gate. Pay attention. Applying 3 volts or a logic 1, you know that 3 volts means logic 1, right? Or true or false and stuff like that. True. Right? Once I apply voltage here, the N type transistor will close the gate here. And then it will allow current to flow from this source to the drain. Mhm. So now that means that if I have a voltage source here, if, if I have 3 volts here, and then I close this and then I apply 3 volts here, what becomes of the drain? What value will be at the drain? What will be the voltage at the drain? If I apply 3 volts, that will close this one. And then I have 3 volts connected to the source. What will be the drain? Somebody says 6. Hey! 3 volts, right? This will just close the gate. That's all it does. And then here, you know potential difference, right? You guys, right? Huh? Master, this is your food right now. I'm in your field. So the 3 volts here will be here. Now, if I have 3 volts here, and then here is 0 volts, what happens here? It's 0. Pay attention. You know, let's just what is coming. Now, if I have 0 volts here, and I have 5 volts, and I have 3 volts here, what happens here? Pardon? If I have 3 volts here, what? If I have 0 volts here, why? The greatest. Are you paying attention? Right, so now, this is NMOS. What? This is NMOS. We have the PMOS also. Now, the PMOS is just the opposite of the NMOS. You see a bubble here, right? So now it means that if 3 volts closes the NMOS, what volts will close the PMOS? What volts? So know that if you're working with transistors, you're working with only 2 voltage levels, 0 and 3 volts. Right? So what voltage here will close this for to allow current to flow from here to here? If I said this is the opposite of this, so if I apply a 0 volts here and I have a 3 volts here, what happens here? Huh? If I have a 0 volts here, what happens here? If I have 3 volts here, so it means that this is open. So we are all there, right? So now we're going to see how to use these 2 gates to construct our logic gates, AND gate, OR gate, XOR gate, and stuff like that. Simple. Simple, right? So it's just like a switch. Once you on and off, stuff like that. So you know that at first, right, they were using only at first, right, in the 70s, right, they were using only NMOS to manufacture data systems, only the NMOS, right? Just because the NMOS consists of electrons, while the PMOS uses holes. The electrons were easier to handle than the holes, right, at that time, right? So, but now they are using both. They combine both the NMOS and the PMOS into what is known as the CMOS, complementary oxide semiconductor, right? Now they can handle the holes and then the electrons easily, right? So they use both to construct your data system, your PCs, your watches, and stuff like that. And then that's what it's made up of. Now, this is the simplest logic structure that exists in modern computers. Who has seen this one before? Hurry up, hurry up. Who has seen it before? Have you seen it before? So, so let's pay attention here. If you're not seeing it before. So what happens is that now, if I give you a structure like this, right? What I expect is that you know what the input is. You know what the output is. That's very important. And how many inputs are there? How many outputs are there? Right? And you guys know how to draw truth tables. So I expect you to be able to draw the truth table of this. So what do you so in case you are given a structure like this, how many inputs are there? Master, look here. Don't look at my face at all. Don't look at my face at all. So this is the structure I have, right? Now study it. How many inputs do you think there is? One input. What is the that one input? In A, right? How many outputs? What is it? Out. So what I expect is that now to be able to determine what this does, or what type of gate is it an AND gate, an OR gate, or an XOR? Master, why? Why are you so annoying like that? Hey, you look so annoying like why? Is there anything? What? Hey, what? a level of trust. It means that if I raise it up there, the way you put me out like this, this, this simple thing, but you are so annoying. It means that if I raise that level, but in case you catch me outside. All right, so pay attention. Once you have something like this, very easy. Okay? You just pay attention. You have input, you have output. Just take your truth table. I have my input is A, right? My output is what? Y. Right? And then in case I have only one input, I said in digital systems or in digital system you only have two states, a 0 and a 3 volts, or a 0 and a 1, a true or a false. So if I have only one input, right, it means that I can only have two states, 0 and what? 1. So so pay attention, A can be 0 or A can be what? Right? So what I do is that I take 0 and 1 and then I pass it through the circuit, like how you guys always do during circuits. That concept is called what? Circuit theory or something like that. You break the circuit and then you pass things through it and then you see how the output works, right? That one is an issue. I'm not talking about any practical, but I mean, it doesn't matter. So, what I do is that I take 0. 0 means 0 volts. 1 means 3 volts or 5 volts. It depends on the technology. But here, let's just say 5 volts, right? So I have to take 0 because A is only one input, so I can have 0 or 1. So I take 0, I pass 0 through the circuit, and what happens to the output? Now, so pay attention here. I told you that from the beginning, a 0 turns, you can see that on top is the what? Is the PMOS. Below is the what? NMOS. The PMOS is connected to a voltage source. The, the NMOS is grounded. Are you seeing it? Pay attention. So now, if I apply 0 here, 0 volts here, what happens here? Hurry up, hurry up, hurry up. Just go through the circuit. It's very, very simple circuit. I apply 0 here, right? I apply 0 to the in A. That 0, as you can see here, goes to the PMOS and the NMOS. Are you seeing it? Yes, sir. So if 0 comes to the P, okay, let's start with the NMOS. If 0 comes here, what happens to this NMOS? Huh? It's open, right? So this one is cut off. It's open. Now, if 0 comes here, what happens to this NMOS? So it means that it is on. Yes. Let's just say that. So this one is on. It means that this one is closed, and then voltage, and then current can pass from here to here. So if this is on, this is off. What do you think is the output? 3 volts, and then 3 volts is what? 1. You see how simple that is? Now, if I apply a 1, let's go through it again. If I take a 1 here, if I apply a 1 here, a 1 means a 3 volts. What happens to this? It's open, so it's cut off. It means that you don't care about that part anymore. It's off. Now, if I apply a 1 here, what happens here? It's closed. Now, what do you think is the voltage here? If this is 0, right? So pay attention. It's very simple. Once you are able to understand it from class, that's all. You don't need to go and study anymore. It just sticks. You don't you go. All right. So now this is a truth table. It means that if the input is a 0, the output is a what? A 1. If the input is a 1, the output is a what? What type of gate is this? Not. Or what? A not gate. Or what? An inverter. So you see that because it gets inverse the input, the output is an inverse of the what? The input. If it's a zero, it's a one. If it's a one, it's a zero. This is just an inverter, and then it looks like this. So this is the internal architecture of a NOT gate. So if you draw it like this is the logic gate, and then this is the internal architecture of this NOT gate. You get it?
Yes.
Are you all there? I mean, this is the course for your first year or something like that. Yeah. Okay, so now let's move on. This is the simplest logic gate you can have, the inverter. Right? Now let's move on to a very complex one. So all of this is just trying to explain. So all of this is just trying to explain it, right? Okay, now the same exact way, right? I mean, you teach very simple stuff in the class and you bring the complex ones in the exam, right? I mean, that's what you do that. So I gave you the simplest logic gate, which is the what? The inverter or the NOT gate.
Yes.
Now, once I give you something like this seems complex, but it's very, very simple.
Yes.
Once I give you something like this, you have to go through the same process, like how I did for the inverter, to get your output, to draw your truth table, and then to know what type of gate it is. Right? So how many inputs do I have here? So A and B, right? So it means that all I do is that, so all I do is I have A, B. And then how many possible values of A and B do I have? Ah, now we are two. Now we are two. So I can have 0, 1, 2, 3. 0, 0, 0, 1, 1, 0, 1, 1. 0, 1, 2, 3. So I have four possible combinations. 0, 1, 2, 3. Understood? Now once I do this, then I come and so what is y? When A is 0 and B is 0. Hmm? Pay attention. Pass it through the circuit. If A is 0, if A is 0 and B is 0, what happens here? A is 0, right? So pay attention. A is 0. You see where A is. Right? A connects this one and then this one. So this one is on. And then B is 0. This one is what? On. Now, A is 0 means this one is off. This one is off. So once the top is on, and then the top is connected to the voltage source, it means that the output is it's 1 or 3 volts. So you see how I can easily get this. So always pass it through the circuit, one by one. If not, you get it wrong. This is very easy. Once you make up your mind that you won't understand. You won't understand it. You have made up your mind that it's not too broad. Take the zeros and ones. The basic. Don't come to class and make up your mind that it's easy. And then you can ask me anything. I can even go below this level and this level. Don't just make up your mind that always say, no. That's not how you learn. You are too educated person. Now let's what of 0, 1? If I apply 0, 1, if A is 0 and then B is 1, what happens? Why? Pay attention. Always go through the circuit. If not, you will get, as I said, in digital system, you are getting 100% or 0%. So once of this, once I ask you to load a truth table and then you flip just one of it, the whole thing is wrong. You understand? So if A is 0 and B is 1, what happens? What is up? Now let's go. Now remember, A is 0. A is 0 means that this PMOS is what? It's on. Right? And then A is 0 here means that this PMOS is off. This NMOS is off. So it means that this whole side, once you see that once this one is off, this whole side don't matter anymore. But you see that once A is 1, right, this PMOS is off. And then this NMOS is on. But because there's a hole here, nothing can happen here. And then you see that these PMOSs are in parallel. So even one of them being on will make sure that this voltage appears here. Just one of them. Both of them must be off. Pay attention. Both of them must be off for this part of the circuit to be cut off. Right? Are you seeing it? So if A is 0, it means that this P must be working and then this voltage will just appear here. So 0, 1 is what? 1. Right? So this is 1.
So the next one is 1.
Right? So easy, right? Because we have one of them to be 1, right? It means that one of the pieces is 1 on. So you see how fast he is. Very, very fast. So here is 1. 1 is what? 1 1 1 1 1 1. Why? So this place is the top. The top is off, the down are all on. So this voltage will be here. So this is a 0. So this gate, the truth table for this is simply this 1 1 1 0. Now I must know what gate it is. So do you all understand? Do you all understand? Who does not understand? And then, as I said, once you don't get it from the class, I mean, forget it. If you're going to waste your time reading, I don't have any idea. But always gets fast once you know that once, and pay attention once. This is just how they all look like, right? The top ones are always the P mosses. The P mosses are always arranged in parallel. The down ones are always the N mosses. The N mosses are always arranged in series. Right? I hope you are all there. Yes. So what gate is this? 1 1 1 0. What gate is it? NAND. Right? Do you understand how we have the NAND gate? Yes. No. No. Please pay attention. Do you guys understand why he had a NAND gate? No. So this gate is known as the NAND gate. The NAND gate means what? Please pay attention, pay attention. What is the NAND gate? Not AND. So all we do is that if this was an AND gate, right? What would be the truth table? Here will be what? 0 0 0 1, right? But once you see that this is an inverse of this, right? So this is a NAND gate. A gate are in this. Not AND. Simple, right?
Yes, not
Shall I continue? Okay. So this is the NAND gate. And then I've even explained it a lot. So if you don't understand, you can just go through this one and then you will be fine. Okay, so if this is the NAND gate, right? How will the AND gate look like? What must I do to this one to make it an AND gate? Uh-huh. But oh, what must so this is the NAND gate. I said it's not AND. So what must I do to this gate to make sure that it is an AND gate? It's very simple. Common sense, but which is not common to people. But I must people say anything stupid. But okay, put one. Put one. Master, I'm waiting for you. Put what? Do you want your 5 marks or not? Okay, another. Hey, master. Anybody? Okay. Yes. Pay attention, pay attention.
Because it is not relatively because it is not
Yes, right? Common sense, right? So if I want to turn this into an AND gate, we saw how the inverter works, right? So I just put a NOT gate at the output here, and then I'll turn it into an AND gate. Was that what we're going to say?
Yes. Yes.
So this how it looks like the AND gate. You can go home and pass it through and pass 0001102 and see how it works. That's your choice. Now, the most important thing is that you have seen three gates: the NOT gate, NAND gate, and then the what? The AND gate. You've seen how to use the transistors to construct this basic gate, right? And then with these gates, you can design any system you want, right? But it means that I can use the NAND gate to design any system I want. I can use the AND gate. Pay attention here. I can use the AND gate to also design any system I want. But then you must know that if you look at the architecture of the NAND gate and then the AND gate, right? In case I'm designing something and then I'm using more AND gates, right? It means that my hardware area, we call it the gate count. Like if you design your hardware, right? The hardware, they are going to count the number of transistors in your hardware, and then that's going to be the cost of the hardware you're actually designing. So the cost of your hardware is actually directly proportional to the number of gates within your system, right? So if I design a system that has a lot of NAND gates, you see that the NAND gates have two more transistors than the NAND gate. It means that your hardware area is increasing, the cost of your product is also increasing. So normally we design our stuff with mostly NAND gates so that the number of transistors are reduced and then the cost of the product is reduced. That's what makes you a good engineer or a bad engineer. Right? Shall I continue? And then the last thing is, who has heard of the Moore's law before? Not more. Who has heard of it? Who has heard of the Moore's law? You've never heard of it in your life. So, what happens happened is that during the early days of the transistors, right, there was an engineer called Gordon Moore. Gordon Moore, right? So he saw that he envisioned that, Master, he envisioned that in 1965, right, he saw that the number of transistors is going to double every 2 years. Yes. So each product coming out every 2 years will have more transistors, like twice of it. Right? Yes. Now, if we study that trend, it has been true for a very long time. If we study the trend for the Moore's law, right? From 1965, every 2 years or every 18 months, the number of transistors on the chips will double. But it has gotten to a point from around 2005 that the number of transistors have become a little bit stable. They are not doubling anymore because it's very difficult to double right now, right? What happens that all they are doing is they are reducing the size of the transistor. And then if you see the transistor, it looks like this, the one that the one we have been doing, right? This portion of the transistor is known as the channel. All they are doing every year was that they were reducing the channel, right? Reducing it, and then they're able to pack more transistors into the same die. But it has going to a point that they reduce it to the point that it has become so small that there is leakage current without the transistor even being on. There is some kind of leakage from the source to the drain without you even turning this one on. So they cannot reduce it any further. That's one thing. That's one. Now, if you pack so many transistors into a die, right, it produces a lot of heat. So they are also having issues with heat. So you can say that from 2005 going, the Moore's law have actually slowed down. But at first, it was true from 1965 till 2005. It was true every year, every 2 years, it happens, it happens. But now they're having so much difficulty that how to actually reduce the transistor has become very, very difficult because of leakage voltages and heat. Interesting. Pardon? Any question? Any question? Wonder what? No. It doesn't decrease. What is the? What do you mean by the quality? They are using what? They have reduced it actually. So they have reduced it and the number of that thing you're talking about, the silicon to manufacture one. So they've done well by even using less silicon to to do just one. So the quality doesn't reduce at all. It's just that the difficulty is once it's so close, the source and the drain is close. As an electrical engineer, there's leakage without it being on. Once you put a voltage source here, without it being on, and then it's so close, you see that there's a kind of leakage. So that's their main difficulty.